All right, so 4.6. Actually, one of my favorites. I like the word problems. I like to see where this stuff actually works in the world. I know a lot of you guys are going to probably be engineers or something in the sciences, so it would be nice to show that this actually has applicable use that is done every day. So, what this is 4.6 is applied optimization, which is extremely important for the world because it saves us a ton of money. So, problems. So we're going to start with just some really simple ones to kind of ramp it up a little bit more and more. So, example one. So, an open-ended box is made by cutting out a square at each corner of a sheet of 10. Measuring, that's not how you spell measuring. Measuring 12 inches by 12 inches. So, the question is, how large should the sides of these squares, these cutout squares be? These cut squares be. All right, so to show you what we have here is a lot of these are very pictorial. So what I have is I have a sheet of 10 right here. It's going to be 12 inches by 12 inches. So this is 12 by 12. What we're going to do is we're going to cut out some squares from each corner. So I'm going to cut a square out of this. I'm going to cut the exact same size square out of this, exact same size square out of this, and then here as well. So I'm going to chop those away. So what you're going to get is something that looks more like this now. So that's what we have now. Now remember that this entire side is still 12, and same thing with this entire side is still 12, but these cutouts are, I'm not sure what they are. So what we're going to have is, each one of these, the question is, how big do those sides have to be? This is all going to be X, this is all going to be X as well, and so on. So when we, what we're going to now do is we're going to fold this thing up at these dotted lines, just to show you that I'm building a box here. So what's going to happen is it's going to now look like this. It's going to have this box is going to be built. So when you fold these things up, and fold this up, it's going to turn into this box. So the question is, this is length, this is width, and this is height. What do those have to be? What did each one of these have to be? Okay, so let's figure out the width real fast. We can see that this would be, this part right here, or this part right here, would be this L. So this is going to be L. And this part right here and this part right here would be equal to W. And then our height would be what these X's are. So these really are our heights. So let's get some dimensions. What are the dimensions? Well, I know that the original dimension, that this was 12, right? And if I cut out two of these H's, that means my L is going to be equal to 12 minus, remember I'm cutting this out and this out, so minus 2H. My width is the exact same thing. This is my width, but I'm also cutting out these two things. So the width, which would be 12 minus this and minus this, which would also be 2h. And then my height would be equal to h. So my goal is to write the dimensions of this box using just one variable. So that means the volume of this box, which would be equal to length times width times height, is now going to be equal to 12 minus 2h times 12 minus 2h times h, right? So what I'm trying to do is I'm trying to maximize that would have been really good information to kind of go on. So what I'm trying to do is I'm trying to maximize the volume of this box. So in order to maximize the volume of the box, I need an expression for the volume of the box. And remember, when we maximize, what we just did with curve sketching is if you want to find local max and local minimums, what I'm going to do is I'm going to find the derivative of this thing, and I'm going to set it equal to 0. That's where local max and local mins are. Once I have the derivative equal to 0, I'm going to plug those zeros into the second derivative. If it's concave down, I mean concave up, it's a local minimum. If it's concave down, it's a local maximum. So that's kind of our goal here. So multiplying this together, I have, this is going to be 144 minus, this gives you 24. And this also gives you another 24, so minus 48h plus 4h squared, also times h. Oh, I get 96. Oh, there you go. Times h. So this is going to be equal to 144h minus 48h squared plus 4h cubed. So this is actually a really easy expression because it's a polynomial. So what I want to do is I'm going to take the derivative of this expression again, and I'm going to set it equal to 0. So we know that again v of x is equal v of h is equal to 144h minus 48h squared plus 4h cubed. So that means v prime of h is going to be equal to 144 minus 96h plus 12h squared. And I'm going to set this equal to 0. So v prime of h is equal to 0 for a critical point. So 144 minus 96h plus 12h squared equal to 0. What's nice is this is a quadratic, so you could use the quadratic equation, but I think it factors nicely. So if I factor out a 12, I'm going to be left with 12 minus 8h plus h squared. And I don't like them like this. I'm going to switch this around. H squared minus 8h plus 12 equals 0. So it's easier for me to do it in descending order. So I need two things that multiply to this with add to this. So I'm seeing a minus 6 and a minus 2. So 12, this is h minus 6. H minus 2 is equal to 0. So what I get is I'm going to have h is equal to 6 for this one, and h is equal to 2 for this one. Now I want to know if they're maxes or mins. So what we can do is we can plug these things into the second derivative. So I know that v double prime of h would be equal to taking the derivative of this, would be minus 96 plus 24h. So v double prime of 6 is going to be minus 96 plus 24 times 6. Which I think is 96. Minus 96 plus 24 times 6. Nope, I lied. This is equal to 48. Positive concave up, right? Positive concave up. So since it's concave up, because this is positive, concave up, That means x equals 6 is a local minimum. Now, let's try 2, not h. So, v double prime of 2 is going to be equal to minus 96 plus 24 times 2, clearly negative minus 96. I get negative 48, so this is negative, so concave down, so it looks like this. That means it's a maximum. So it means h equals 2 is a local max. So let's kind of go back and see what this means. So I know that this is my answer, right? So that's the answer that I was going to get. Now if we go back here and have a look at this box, what I know is what's kind of interesting is the fact that when you change the size of these squares, that this volume actually changes, so that you can maximize everything. So what's kind of interesting is if you look at like for instance like a coffee can, or like say cans of pop, for instance. Like if you look at like Coke cans or Pepsi cans, you know, why is all the shapes of our cans or all the shapes of our waters, you know, basically the same shape? Now I know some of it has to do with the way we shelve things, but a lot of it has to do also with maximization. Like why is it always the exact same size? Remember that plastic or metal, you know, costs money. So if you want to maximize the volume but minimize how much material you need, you know, there's a particular dimension that actually does that for you. You know, I wouldn't make this extremely long and then very skinny, because it's going to take a heck of a lot of material to give me very little volume. And also, I'm not going to make it really short and really fat for the exact same reason. Little volume, a lot of material. So there's an optimal shape for everything, and that's why we do this. So the optimal shape for this to maximize means I have to cut 2 out of this. To cut 2 by 2 squares. Actually, if you look at the domain of this, the domain of these cuts, the smallest h that you can cut out is 0, because you would have just a box, right? You just have an open box with no height. And the most that you can cut is 6, because if you cut 6 from here and 6 from here, you've got nothing left. You know, all you have is 4 squares now. So that also gives you a volume of 0. So you do still have to look at your domain. That's why, you know, 6 of course is going to be a minimum, because there's nothing left. You know, you're going to get a volume of 0. So if you try to plug 6 back into here, into this volume, it's going to give you 0. So now just some work with functions. This is to practice this marrying multiple functions together to find their derivative. So inscribing a rectangle. So what is the largest rectangle? Inscribing a semicircle of radius 2. So what I'm going to do is I'm going to draw a picture. We're going to put function notation on each one of these. So what I know is I have a semicircle of radius 2. So I'm going to graph a semicircle of radius 2, and I'm going to do it on some axes that are really nice. So I'm choosing the center of our circle to be 0, 0. So this is going to be my circle of radius 2. So here and then here. So there's our circle. Radius 2 means that this is going to be at x equals 2. This is going to be at x equals negative 2. And same thing for the y equals 2. Alright, so what I want to do is I want to inscribe a rectangle inside of this particular expression. Well, I'm just going to draw a random rectangle in here. So this random rectangle is clearly not going to be, it might be the maximum, but so inscribing means that your vertices are going to be on the circle, and that's what we mean by inscribing. So that's actually a pretty good rectangle. I bet you that's close to our maximum. So what I need is I need some functions on here. Well, we know that the circle is x squared plus y squared is equal to 2 squared. That's, that's circles x squared plus y squared is equal to r squared. So I know the circle is going to be y squared, which would be equal to 4 minus x squared. So y is going to be, well, the top half is the positive root, and if I wanted the bottom half, it would be the negative root. So that right there is the circle. So let's talk about this point right here. This point right here is x comma y, right? Just a point on the circle, but it can't just be any x comma y, because if it was any x comma y, it could live anywhere here, right? So how do I force this point to live on the circle? Well, you force the point to live on the circle by using this x value and using that y value. So technically, this x value is really x comma root 4 minus x squared. So that's really that x value. That forces this point to live on that circle if you use this x value and that y value. All right. How do you find the area of the rectangle? Well, the area of this rectangle is going to be base times height, right? So it's going to be base times height. Well, what's the base of this thing? Well, if you look at this rectangle is tied to this point here, right? This rectangle is tied to this point. So the area of the rectangle is going to be equal to base times height. Where the base of this thing is, this is our base, right? Well, since it's tied to this point, I know that this is x, right? So this distance right here is x. So in order to get the entire thing, I need x, and then I also need another x. So the base is 2x. And the height is, well, this is going to be y, right? This is going to be our y value. So this is x, and this is x. So that's why we get 2x. And this is going to be y. So that means the height is just y. So the problem here is when I'm trying to do this entire section, I need to avoid having two different variables. What I need is I just want one variable here. So in order to do that, I know that this point technically is x comma y, but y is this thing. So really, this area is equal to 2x times y, which is 4 minus x squared, because the y value is on the circle. So our area is equal to 2x times the square root of 4 minus x squared. So now if I want to find the critical values, so this is because we're asking for the largest rectangle. So what I want to do is I need to take the derivative. So a prime, derivative of the first times the second plus the first times the derivative of the second. Derivative of what's inside. Clean this up because remember I need to know where this is equal to 0 or undefined. Because I want to find the critical value. So this is going to be 2 times the square root of 4 minus x squared plus multiplying these two together. So actually I'm going to get a minus here because this is negative, this is positive. 4x on top, and then I'm going to have 2 times the square root of 4 minus x squared on the bottom. Alright, cleaning this up. I need to top and bottom by this denominator, so 2 root 4 minus x squared over 2 root 4 minus x squared. This looks familiar because we've done problems just like this. Taking derivatives of these things instead of equal to 0 times 2 minus. So when I multiply these two together, you're going to get 2 times 2, which is 4, times this, be careful, parentheses, 4 minus x squared. Minus 4x all over 2 times square root of 4 minus x squared. So let's I can fix this too. Let's call this 2. So this goes in this twice. Well, never mind. I'll clean it up later. This is going to be 4 over 2. It'll be fine. I'll take care of it later. So when I multiply, this is going to be equal to 16 minus 4x squared minus 4x squared all over 2 times the square root of 4 minus x squared. So what we're going to get is we're going to get 16 minus 8x squared all over 2 times the square root of 4 minus x squared. And I could actually cancel the 2 into all these things. So this would actually be 8 minus 4x squared all over just the square root of 4 minus x squared. The algebra would have probably been a little easier if I would have canceled that. I wouldn't have had to have this 2 here. But it all goes away anyway, so this is fine. All right, so this is our expression. Now, since this is a prime of x, I need to find when this thing is equal to 0 or undefined. So a prime of x is equal to 0 or undefined. So remember that the derivative 4 minus x squared all over 4 minus x squared is going to be equal to 0. This is when the numerator is equal to 0. 4 minus x squared is equal to 0. So something 4 over 8 is equal to 4x squared divided by 2. So x is going to be equal to plus or minus root 2. Now where it's undefined is when the bottom is equal to 0, so 4 minus x squared is equal to 0. Usually the undefined part we don't worry about because it's not usually in the domain, but I'm going to do it anyway just for practice. So x is equal to plus or minus 2. But they should be considered because every now and then, like I said, usually this doesn't matter, but every now and then it does. What's funny is that clearly is actually a minimum, and these will be maximums, and I'll kind of show you. Second derivative. I'm not sure I want to take the second derivative of this thing, because derivative of the top times the bottom. Yeah, you know what we can do? Instead of doing the second derivative test, let's do the first derivative test. Because I think it'll be a little less work than taking the derivative of that again. But you're welcome to do the second derivative and plug those 4 points in and see what you get. But the first derivative test knows that I'm going to have, these are my critical values. I have negative root 2. I have positive root 2. I have negative 2. I also have positive 2. So let's check these intervals and see what happens here. So remember, our intervals would be minus infinity to minus root 2, minus root 2 to minus 2, minus 2 to 2, 2 to root 2, 2 to root 2, and then also root 2 to infinity. So picking x values in here, know that root 2 is about 1.41-ish. So I'm going to pick, for the x value, negative 2. Is that right? Oh, I got these backwards. Garr. Sorry. Those are backwards. Let's try this again. It would be negative 2, and then negative root 2, and then root 2, and then 2. This is 1.41, and this is 2, so it's bigger. So my intervals are backwards. Minus infinity to minus 2. Minus 2 to minus root 2. Minus root 2 to root 2, and then I have root 2 to 2, and then finally 2 to infinity. X values, and remember we're going to do f prime of x to figure out if it's increasing or decreasing. So I'm going to pick negative 3, I'm going to pick, I'm going negative 1.9. I'm definitely going 0 there, 1.9, and then I'm also going to pick 3. Now I'm going to plug these into the calculator, so this right here, so y equals that mess, so 8 minus 4x squared, close parentheses, divided by second square roots of 4 minus x squared. Enter, and then we're going to go to our table and plug in these values. So negative 3. What's kind of cool here is this is going to be an error, because if I already know this, because if we looked at the domain of this expression, the x values, the biggest x you can get is 2, the smallest x you can get is 0. And if you look at the domain of this expression, that verifies it. Like 4 minus x squared has to be greater than or equal to 0. So that means x is going to be stuck between plus or minus 2. So that's the domain of the green. So I already know before plugging this in, if I plug -3 into this derivative, this is going to give us an error. But, error, okay. I wanted -3. So then I'm going to pick -1.9. If I can fix my fingers. 0. I don't think it's, yeah, you can see this. 1.9. And then 3 again. I know it's outside the domain, so we're going to get an error. So we already know that those are outside the domain, so I don't really care about those. So what I know is it's negative here. So this is it's negative here. It's positive here, and it's negative here. So what I know about the sketch of this thing is it's going to look like this, and then it's going to look like this, right? So if you did plug this in the second derivative, you know it's going to be concave up, and this will be concave down. But that means this negative root 2 is a let's make sure we're good here. Negative, positive, negative. I'm good with that. Let's see. What do we get for? Okay, whatever. We're gonna finish this. So that means x equals root 2 is a local max. I can live with that. So if I go over root 2, and I'm kind of curious what the y value is. Let's find the y value. So what about y? Y is going to be equal to the square root of 1 minus, it's 4 minus x squared. I just want to know the dimensions of the rectangle. So this is going to be the square root of 4 minus root 2 squared. I should have did that. 4 minus 4, y is going to be equal to 0. That's not true. Nope, thank goodness. This is going to be equal to the square root of 4 minus 2, which is equal to also root 2. Cool. Okay, so what I know is I know that the coordinates of this, the coordinates of this point right here is going to be over root 2, up root 2. So this is going to be root 2, comma root 2. So that means our dimensions are, remember this is the base is 2 of these. The base is 2 of these. Is going to be equal to 2 root 2 by root 2. So if you want to know the volume or the area of this thing, it's going to be equal to 4. You're going to multiply those things together. Maximizing profit. Some of you guys are going to be business majors. You might as well see a business example. So, all right, maximizing profit. We all want to do that, right? It's maximizing profit. Suppose that our revenue, our R of X, is equal to 9x. So this is our revenue. And our cost and C of x is equal to x cubed minus 6x squared plus 15x. This is our cost. Now we know our profit. So just to make sure you guys understand. Revenue is how much, this is the money that you get after you sell your wares. So remember that just because you sold all your stuff and have your money, it doesn't guarantee that you've made any profit. Because if I make 1,000 things and only sell 2 of them, so you're going to be, you're not going to reap how much money that you put into making your materials. So what you want to do is you want to, if you want to find your profit, it's your revenue and then it's minus your cost. It's how many things you sold after you subtract off how much you put in to make them. So profit is equal to revenue minus cost. So P of x is going to be equal to this minus this. So it's going to be 9x minus this x cubed minus 6x squared plus 5x. So we're going to have 9x minus x cubed plus 6x squared minus 5x. So this is going to be equal to 6x squared. No, I want to do the x cubed first. So negative x cubed plus 6x squared plus 4x. That's P of x. So what I want to do is I want to maximize this. So we're going to find P prime of x. So this is minus 3x squared plus 12x plus 4. And then of course I'm going to set it equal to 0, right? So since this is quadratic, factor out that negative 3. This is going to be minus 4. Oh, I can't factor out negative 3. It is not pretty. Okay, well unfortunately, x is going to be equal to, finding the zeros of this, is going to be minus 12 plus or minus the square root of negative 3 squared minus 4 times a times c all over 2 times a. So I'm going to get, make sure that my work is correct. We have 9 minus 4 times 57, huh? Oh, it doesn't matter. I just got it. Okay, so this is going to be equal to minus 12 plus or minus the square root of 57 all over negative 6. So horrible, horrible numbers. Whatever, it's going to be fine. So minus 57 is, I don't see any perfect squares in there. So what I'm going to do is I'm just going to kind of give us decimal approximates for these. So minus 12 plus the square root of 57 divided by negative 6, and then I'm going to find the other one, minus. So I get, this is, I get about 26.7, that's good enough for me, and I also get 117.3, I'm rounding, the numbers are too ugly to carry. So those are your x values. So if I want to know what's going to maximize my profit, I need to, I can stuff these into the second derivative and see what happens. So I'm going to see if it's concave up. The reason why I'm doing the second derivative test is because it's a polynomial, and it is super easy to take the derivative of that thing. So this is going to be minus 6 times 27 plus 12. So I'm testing this one first. Clearly that's going to be negative, right? Double prime of 27.6. Oh, I got a problem here. I'm seeing 2 negatives. There's got something got to be off here. Oh, that's why. I have not done that correctly. Those were wrong. There we go. These numbers were wrong. I get, one is 3.25, 26, and the other one I get 0.74. So plugging those both into the second derivative. So this is minus 6 times 3.26 plus 12. That's looking negative. Minus 6 times 3.26 plus 12. Yep, this is negative 7.56. This is negative. And for the other one, minus 6 times 0.74 plus 12. This is positive. This is equal to 7.56. So this one is positive. So what I have is this one is going to be concave down, and this is going to be concave up. So since it's concave down, that means 3.26 is a maximum, and that's what we're trying to do. So x is equal to 3.26 units. Whatever they're selling, they must be expensive. I was hoping for a much bigger number, but it is what it is. So actually, you can't sell 3.26 units. You can only sell, well, that's actually something we should talk about. I'm not sure if the book will hammer us on that, but you can't sell 0.26 of a unit. So in order to maximize, you have to sell at least this many units, and 3 is not going to cut it. So technically, you would have to sell 4 units in order to maximize your cost, because you have to sell at least this much. So the book might give you this, but that's real life right there. You technically have to sell at least that many. I'm going to give you one more example. I stole it from another book. I don't know if I can find this one. Let's see. I think I can reverse engineer this. Okay, so I want to. Okay, I got it. So this is actually number 23. It might be your homework, but yeah, we're going to do it anyways. So it says, I'm just going to project this. You know what, let's do this here. So this is number 23. So it says a silo base not included. Base not included is to be constructed in the form of a cylinder surmounted, so mounted on top, by a hemisphere. So like a silo, you know. It's got a cylindrical bottom and it's got a spherical top. Okay. The cost of construction per square unit of the surface area is twice as great for the hemisphere. What they're saying is that the top of the thing is expensive. as the cylindrical wall. Sidewall it says, but determine the dimensions. The dimensions to be used if the volume is fixed and the cost of construction is to be kept at a minimum. Okay, so it says don't worry about the thickness. So neglect the thickness of the silo and waste in construction. So trying to simplify the problem. All right, so what we know is we have a silo. So a silo is going to look like this. It has a spherical top, and then we have a cylindrical bottom. So there's our top with a cylindrical bottom, right? So there's our silo. Now we have our two parts here, so we're going to have this cylinder. We have our cylinder, which looks like this. I'm kind of cutting it because this is what we're going to do. So our cylinder, which is wrapped like this, you can actually open it up to be able to figure out how big the cylinder is. And what you know is that the cylinder is going to be the circumference, and the circumference is going to be equal to 2 pi r, and then this is going to be our height. Now for a hemisphere, the spherical part of this thing, so actually I should talk about that. It means the area here. Area is going to be equal to 2 pi r h. And for the top, the volume of a sphere. Actually, is it the volume? I don't want the volume. I want the area of a sphere. So we gotta look that up because we're doing it for area. Okay, Google. Surface area of a sphere. So area of a sphere is 4 pi r squared. So that means the area of the top is going to be, so for the spherical top, for this part, our area is going to be half of this 4 pi r squared, 4 pi r squared. So this is going to be 2 pi r. It's kind of interesting. 2 pi r squared. That makes more sense. Okay. We'll get through this. So what I know is the cost is dependent on let me think through this. Okay, so those are our two areas. It says that it's a fixed volume. So since it's a fixed volume, we know that the volume for this of the cylinder, so for the cylinder, volume is equal to pi r squared h, and for a hemisphere, the volume is going to be half of 4/3 pi r squared, so it's going to be equal to, volume is going to be equal to 2/3 pi r cubed. Alright, the reason why we care about this is because this volume is fixed, so it's going to allow us to, we have two variables here. I have r and h, and I only need one of them. I only want to represent it as one of them. So since the volume is actually fixed, our volume is going to be equal to pi r squared h plus 2/3 pi r squared, and our, so this is that, and I know that our area is going to be equal to the addition of these things, so it's going to be equal to this plus this, so 2 pi r h plus 2 pi r squared. Okay. Since this is a fixed volume, that means this is a constant. So if I just said this was equal to like 10 or something, what that means is I could solve this thing for r in terms of h. So if I want to find h here, h would be the easiest to find. So I could set this over here. So volume minus 2/3 pi r squared would be equal to pi r squared h. So that means volume minus 2/3 pi r squared all over h would be equal to, so all over pi r squared would be equal to h. Again, since this is a constant, that means I can represent h as a function of r. Because again, what I have is if I want to take the derivative here, the problem with finding the derivative equal to 0 is I have two different variables here, and all I want is one in order to use our tests. So really what that means is this h is now going to go into here, so our a is now going to be 2 pi times this ridiculous mess. So let me rewrite this. I got an R here. R. I got an R right there, so there should be an R. So when I rewrite this, I have area is equal to 2 pi r times v minus 2/3 pi r cubed all over pi r squared plus 2 pi r squared. All right. Some of this will cancel, so these pi's will cancel, one of those r's will cancel, so I only have a single r in the bottom, so this is going to be, I'm going to multiply this 2 through, so this is 2v all over r, that's what I'm going to get here, minus multiplying this through over r, I'm going to have 4 over 3 pi r cubed all over r plus 2 pi r squared. So I have 2v over r minus 4 pi r squared over 3. So this is going to cancel. And then plus 2 pi r squared. That's much nicer actually. So this is A. So what I want to do is I want to cost of this. I didn't take that into account. I'll clean it up. Let's go back to where we have. I apologize. So am I gonna have enough time? We will. We'll fix this up. Problem is the cost of I might have to fix this. The cost of this is dependent on the top is twice as much as the bottom. So I needed to take that into account since the cost is equal to 2 times the top plus the bottom. I know that the top of this thing is represented by awesome. Top is this thing right here. So this is the top part of it. So my cost is, I'm going to have to double that number right there. So the cost of this is actually going to double this number. So I'm just going to say 2 times this number. So this is going to become a 4. This is going to become a 4. All right. So the cost with respect to area is going to be equal to, so put this down here. So this T is this one, this base is this one. So our cost is going to be equal to, it's dependent directly on the area, is 2v over r minus 4 over 3 pi r squared plus 4 pi r squared. Okay, so I can add these two things together, right? So this is going to be equal to top and bottom by 3, so this is going to be 12 over 3. So this is going to be 2v over r plus 8 over 3 pi r squared. So that's C. This is also the same thing as 2v r to the minus 1 plus 8 over 3 pi r squared. And the reason why I'm doing that is because I'm going to take the derivative of this, knowing that volume is a constant. So C prime, pulling out the volume and taking the derivative of this is going to be equal to minus r to the minus 2. And then the derivative of this is going to be equal to 16, because remember this is a constant, over 3 pi r. And I'm going to set it equal to 0 or undefined. So this is going to be equal to 2v over negative 2 over r squared plus 16 over 3 pi r. Well, I set it equal to 0. I need the 0 undefined. It would be better if I combined these two fractions. So in order to combine them, they have to have the same denominator. So in order to do that, I'm going to multiply this by 3, and I'm going to multiply this bottom by r squared. So doing that, I'm going to get minus 6v over r squared, 3r squared, and multiplying this one, I'm going to have plus 16 pi. I need top and bottom by r squared, so this would be r cubed over 3r squared. So I'm going to get minus 6v plus 16 pi r cubed all over 3r squared. And it's a lot easier to find where this is equal to 0 because of these things are combined or undefined. So this thing will be equal to 0 when the top is 0. 6v plus 16 pi r cubed is equal to 0. And when it's undefined, this is when 3r squared is equal to 0. So clearly if r is equal to 0, this thing is, I'm crossing it off, because we're definitely not going to have a radius 0 silo. It won't give us any height. So solving this for r means that 16 pi r cubed is going to be equal to 6v. So r cubed is going to be equal to 6v over 16 pi. So r is going to be equal to the cube root of that thing right there. And that right there, I'm just claiming that's the maximum. If you find any errors in there, let me know. But we're running skinny on time, so that's that for this section. That's about as complicated as it can get. So.